Welcome to this short video where I'll show you how to use the Network Composer from the SINEC Advanced Network Suite to plan the network of a small production site and prepare it for commissioning. I am Aylin, your virtual AI avatar, and will guide you through this video. Using the example of a fictional cookie factory, I'll demonstrate the use of templates, what the term device type mapping means, what technologies are, and how to describe and calculate network segments. In doing so, we'll use MRP and RSTP to establish redundancy within the network. The production areas will each have their own network segments, but they will still be interconnected through routing. Finally, to prepare for commissioning, we will generate device configuration files that are tailored to the end devices. In the cookie factory, now being planned, the network will be designed to cover 4 productive areas. For this purpose, network templates are used, which are specifically provided for the factory automation section within the Network Composer. The factory itself will be divided into 2 main areas, production and distribution. Each of these areas requires its own aggregation network, ensuring reliable data communication and connectivity throughout the factory. In addition to the aggregation networks, the backbone itself, where the central router is located, is also available as a network template. All these components can be quickly and easily integrated into the topology using a simple drag-and-drop approach, making the network setup both straightforward and efficient. After the templates have been placed, connections between the different areas are created. This is done by simply dragging and dropping lines between the ports. It's important to pay attention to how the ports are labeled. For example, the port labeled aggregation on the backbone is specifically intended to connect to the aggregation network. The corresponding port on the aggregation side is labeled backbone. Since these ports are specially prepared for this task, it's essential to follow this convention as closely as possible. Templates don't contain specific devices, but only placeholders that describe the physical and functional requirements. That's why the next step is called device type mapping, where these placeholder devices are replaced by the actual devices to be used. To do this, the devices to be replaced are selected, and the device type mapping function is used. Only those device types that meet the required specifications are then offered for selection. This step has to be done for all network components that shall be configured in the following steps. After mapping the device types on the aggregation and backbone level, the cell firewalls are now replaced by specific devices. Also in this case, we just select all of them and trigger the device type mapping feature. In this case, we have chosen the Sklance S615 as a cell firewall. The network templates are already designed to include technologies that are well suited for this context. These technologies are represented as so-called configuration domains. In this initial step, only the technically feasible technologies are identified and visually highlighted in the topology by selecting the corresponding configuration domain. This step does not involve calculating specific parameters or making final decisions about which technologies will ultimately be used. The final decision as to whether a specific technology will be applied is made in a later step called network configuration. To prepare for the eventual calculation of concrete parameters, groups of devices that represent logical instances of the corresponding technologies needs to be done using the Calculate Configuration Domain feature. These calculated instances can then be individually highlighted in the topology. Network segments are used to define which layer second network's devices and network components should be accessible in. In our example, we have a backbone network, an aggregation network, and an individual network for each cell in the production area. Since the templates already include pre-configured network segments, only minor adjustments need to be made. In this case, all production cells currently have the same IP range because they were created from the same template. We want to change this so that each production cell has its own unique IP range. To move individual network segments to a different IP range, select the desired network and change the IP address of the subnet. The system will automatically apply this change to all devices within the selected network. Repeat this process for each cell in the production area to ensure that every cell has a unique IP range and VLAN. Now that each device has been assigned to the appropriate network segment, it's essential to ensure that all gateways, virtual local area networks, and static routes are properly configured to establish full and consistent connectivity between all participants. This can be done using the Calculate Network Segment action. When you select all available options, the calculation will not only create complete connectivity, but will also merge network segments that belong together, such as the aggregation segments in this example, and removes any empty segments that are no longer needed. This process is highly complex, so in this video it has been sped up by about 1 minute for demonstration purposes. The result is a completely consistent network where all participants can communicate with one another seamlessly and reliably. In this step, we're going to calculate the actual parameters for the MRP configurations. Previously, we calculated the corresponding configuration domain, MRP, in order to identify the logical instances involved. Now, to configure all the parameters for the devices in the ring, we'll start by selecting individual participants from each ring. Once the participants are selected, we go to the Network Configuration section and create a new intent. We give this intent a name, and in the next step, the system searches for all the devices involved across all rings. It then checks if there are consistent config domains available for these devices. In our case, there are, which means the software can now calculate all the MRP parameters for every device in the ring, as we can see here. It's important to note that the system doesn't just calculate the direct MRP parameters. It also calculates associated values. For example, in certain scenarios, spanning tree is automatically disabled to ensure a consistent configuration for all devices. This comprehensive calculation ensures that every device in the ring is properly configured for MRP, resulting in a robust and reliable network setup. Now, we're going to design the redundancy protocol, rapid spanning tree, for the backbone and aggregation networks. These networks have already been pre-configured and prepared through the corresponding config domains. Here, 2 individual devices are selected from the desired RSTP network. We then create a new network configuration of the type intent. Once that's done, the system can automatically generate and calculate all the necessary parameters to implement the redundancy exactly as needed. In advance, we've already determined which device will be the primary root bridge and which one will be the secondary root bridge. Likewise, we've defined which links should be blocked under normal conditions to ensure proper redundancy and a robust network design. In the area called Version History within the main navigation Intent Enforcement, you can activate the current in-work version and apply it as the target state. This lets you continue working on network without altering the current state. To do this, simply use the Set to Active function. Now that all parameters are ready and the network is consistently designed, you can create configuration files for the devices. In the Device Intent section, simply select the devices, click Export Config File, and the system generates them for secure download. In the Documentation section within Intent Enforcement, the software offers several types of information for download. This includes the connection diagram for each device, an overview of all assets, and the complete topology. These documents can be exported within a defined scope, either for the entire topology or just for a specific subgroup or device area. That brings us to the end. I hope I was able to show you how the SINEC Advanced Network Suite can be used to design, configure, and commission a factory communication network. I wish you lots of fun and success in recreating these steps. Goodbye.